Humanoid robotics has entered a new phase of development, where machines are no longer designed as simple tools, but as adaptive systems capable of learning from their surroundings in research laboratories around the world. Engineers study how these robots move, balance, and respond to the unexpected. Each component, from artificial muscles to advanced sensor arrays, is tested under controlled conditions to understand how it behaves under stress. This careful analysis forms a foundation for robots that can operate safely and intelligently in real environments. With every experiment, the machines gain a deeper understanding of motion, stability, and interaction, bringing them one step closer to functioning alongside humans. To build reliable humanoid robots, researchers focus on the fundamentals of movement. Robots practice walking across uneven surfaces, shifting their weight to maintain balance, and adjusting their posture when external forces push against them. These exercises may seem simple, but they are essential for developing machines that can navigate the unpredictable nature of the real world. Engineers record every motion, analyzing how quickly the robot reacts and how efficiently it recovers from instability. Over time, the robot internal systems learn to predict and compensate for disturbances, creating a foundation of stability that future tasks will depend on. Once basic movement is mastered, robots are introduced to tasks that require coordination between multiple joints and sensors. They learn to reach for objects, adjust their grip, and place items with precision. These actions demand a high level of synchronization, as the robot must constantly evaluate distance, weight, and resistance. Engineers design repetitive routines that challenge the robot's ability to adapt, ensuring that it can perform the same task consistently even when conditions change slightly. Through this process, the robot develops a refined sense of control that allows it to handle delicate materials as confidently as heavier ones. In advanced testing environments, robots are exposed to scenarios that simulate real workplaces. They navigate narrow corridors, avoid obstacles, and interact with moving objects. These tests are designed to teach the robot how to make decisions in dynamic situations. Instead of relying on rigid programming, the robot uses learned behavior to evaluate its surroundings and choose the safest and most efficient action. Engineers monitor how well the robot anticipates changes, how quickly it reacts, and how smoothly it transitions between tasks. Each improvement brings the machine closer to functioning autonomously in complex environments. As robots become more capable, researchers introduce tasks that require both strength and precision. A robot may lift a heavy object, stabilize its posture, and then immediately switch to handling something fragile. This contrast is essential for real-world applications, where machines must adapt to different demands without hesitation. Engineers design routines that challenge the robot's ability to shift between power and delicacy, analyzing how to adjust grip pressure, joint movement, and balance. Over time, the robot develops a level of versatility that allows it to perform a wide range of tasks with confidence and accuracy. To prepare robots for unpredictable environments, researchers expose them to controlled disturbances. Floors may shift beneath their feet, objects may appear suddenly, or lighting conditions may change without warning. The robot must analyze the situation, stabilize itself, and choose an appropriate response within fractions of a second. These tests strengthen the robot's internal models of balance, motion, and risk. With each successful reaction, the machine becomes more resilient, capable of functioning reliably even when conditions are far from ideal. This resilience is a crucial step toward real-world deployment. Another key area of development is the robot's ability to understand human behavior. In shared environments, robots must interpret gestures, anticipate movements, and adjust their actions to avoid interfering with people. Engineers create scenarios where humans move unpredictably, change direction, or reach for the same object as the robot. The machine must recognize subtle cues and respond appropriately. Through repeated training, the robot develops a practical form of social awareness, not emotional but functional, that allows it to work safely and smoothly alongside humans. To expand their capabilities, robots are trained to handle tasks that involve planning rather than simple reactions. They must analyze a series of steps, predict potential obstacles, and choose strategies that lead to efficient results. For example, a robot may need to organize scattered tools, identify which items belong together, and arrange them logically before beginning its main task. This type of training teaches a robot to think beyond the immediate moment, evaluating multiple outcomes, and adapting its plan when conditions change. It is a crucial step toward autonomous problem solving. In the final stage of this development cycle, researchers combine all previous skills into complex, real-world simulations. Robots must navigate busy environments, interact with humans, and complete tasks that require strength, precision, planning, and awareness. Engineers observe how well the robot integrates its abilities, how consistently it performs under pressure, and how effective it adapts when unexpected challenges arise. These comprehensive tests reveal how close the robot is to functioning as a reliable assistant in everyday settings. Each improvement brings humanoid robotics closer to becoming a practical part of modern life. As humanoid robots continue to evolve, researchers focus on the subtle details that make movement appear natural. Small adjustments in posture, the timing of each step, and the way a robot shifts its weight all contribute to a sense of lifelike motion. These refinements require countless hours of testing, where engineers observe how the robot responds to tiny variations in its environment. Even a slight change in surface texture or lighting can influence how the machine interprets its surroundings. By studying these reactions, developers fine-tune the robot's internal models of balance and coordination. Each improvement brings the robot closer to moving with the fluidity and confidence of a human being, marking another step in the fusion of intelligence and motion. The journey of humanoid robotics is far from complete, But every breakthrough brings us closer to a future where machines and humans work side by side. What began as simple mechanical experiments has grown into a field driven by learning systems, adaptive behavior, and intelligent motion. These robots are no longer defined by their limitations, but by their potential. They represent a new chapter in technological evolution, one where movement, perception, and decision-making merge into a single, unified form. As research continues, the line between human capability and robotic assistance becomes increasingly blurred. The next steps will shape not only the machines themselves, but the world they are designed to support.